So, and once you install, then you can see the PSpice is named as Captures CIS Lite Edition. And if you click this one, then this window, you can see this window, and there is a session log. Now we need to simply simulate RC network first. So we need to use the new project. Then we need to use analog and mixed circuit. And we need to find a location where we need to save our file. So I choose my another drive. I can create another folder E7301. So one folder is created. I can create another folder inside this. Mention example 1. I create another folder under this directory. And now my saved location, project saved location is this folder. And I can name it. So this is, I can name example 1. So now I have chosen this. Now click OK. So it is better to use a blank project. So this is our schematic area where we can draw our circuit. And right hand side, the panel, this is the part list. And we need to add our R and C component. So now there is no part at the beginning. So we need to add library to indicate the parts. So I can use the analog library, or I can, it is better to all the libraries, so then easier for you. So I just
Excuse me, sir. Can you be a bit slow?
okay.
Okay, sir.
Now okay. Now I can sell. So this is the window. Under this window, at the right panel, we have the part list and other symbol also. I'll go. First, I select the place part. And initially there is no library, so I need to add. Now I remove first. Initially there is a library. I remove. Okay. This is when we click. So this is the initial state. Now I can add. Okay, I need to I just cancel this one. I need to activate my mouse. So that highlighted mouse, so you can see. So now I click part list, add library, then I can Control A, select all the libraries and open. So now all the libraries are there. So now I need to choose resistance. So resistance is under analog part library. And if you go, then we can find R. So I can choose this R here. Now I need to take another component, which is C, capacitance. Capacitance, then if I press keyboard R, it will rotate R. Press R, it will rotate. Now I place this one. Now I need to include source for excitation. So this is a source. First, I will show using sinusoidal. Then later on, I'll need to change the frequency of the signal. Then I'll choose another source. So I can choose this sinusoidal signal. Now I can choose the value of this resistance. For example, I can choose 10K. This is okay, 1 nanometer. I keep it. Now my components are ready. I need to connect. If in order to connect, so I need to place wire, the right panel. Place wire. Then I click this source, connect to resistance. It is now I click and click again here. So I click here, then click to capacitance connected. I click and go through this, click here and click here. So now all the components are connected, but we need the zero voltage reference. So now in the right panel, there is a ground part. So I click this ground and I need to press ground. But this name, if we put the ground, there is error. So the reference voltage must be zero. So zero. Now I place the ground and also I need to connect this ground to this. So now my circuit is complete. So, so my circuit is complete. Now I need to set offset. There is no offset for this signal. So I place the amplitude 1 or I can place any amplitude. For the moment, I choose 1 kilohertz frequency. Now I have exciting my RC circuit with fixed frequency of amplitude of 1 volt. And now I need to see what is the input signal and what is the output signal across the capacitance. Now I need to simulate. In order to simulate, I need to go to the PSpice up there and I need to create new simulation. I can name it any simulation, but I name it AC, then create. So at the bottom, I need to. Now this, when I press the simulation, there are different types of simulation: time domain analysis, DC sweep, AC sweep, and bias calculation. So now for the moment, I'm going to use the time domain. And I don't in, take other button, but I need to choose saving data from initial and where to store because I'm using 1 kilohertz and 1 kilohertz equivalent to 1 millisecond. So I can simulate for 2 millisecond. I can write M also without X. So now I can set. Now there is an arrow key for simulation. I can press this simulation. So now if it is simulation, so this is simulation done. This is the output window, but there is no response. So I can add from there the output response, or I can go to here. Also, because this is highlighted voltage, so there is no DC voltage, also no DC current. Now, in order to see output, so I need to click voltage probe. So if I click the voltage probe, so then I can see this is the input voltage, which is a 2 cycle amplitude of 1. Now, if I click there, and since there is a resistance, our voltage magnitude is going to reduce. And since this is a R and this is a C, there is also phase shift.
Sir, please, what is this green and red color? Can you repeat this?
Okay, green.
Yeah.
Okay,
How did
green.
this appear?
No, okay, both of them. So this is the probe. You need to see the voltage
Oh,
level,
voltage. Oh, okay.
voltage level meter. When you click here,
Hmm.
then I can see this level.
Oh,
So now, because now initially, so now this is blue. You
yeah,
can
yeah.
see now because this is an input voltage,
Hmm.
and so if I add another probe,
Huh.
then I can see there is an output.
Oh,
Correct?
oh, yes, sir.
Now, but there is not that much phase shift. But for example, I change this capacitance value to 10 micro. Now let me see what is the response. Input and so you see the output is, so this is a very large capacitance.
Hmm.
So this is cannot becomes almost zero. So I use 100 nano. Then let me see what happened. You see now,
Oh,
now this is for 1 nano. Nano is same as the input, but for larger value of capacitance, we magnitude
hmm.
reduce, and also there is a phase shift because the peak maximum for input and output is the same. Same
Hmm.
or different? Different, is it right?
That's right. Hmm.
So if it is so they are off. So this is transient analysis. We can see input and
Okay.
output. Output. Just a minute. Hello, hello. Alaikum salam. Hello. Yes. 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 Okay. Uh-huh. So cannot understand Malay. Cannot understand Malay. No, I'm at home. PB8. Yeah. Huh? Where are you now? Where are you now? Guardhouse. Can come to the block B? Okay, okay. Then okay, I'll send my son. Hiroshi, এই সব থেকে নিয়ে আসো। হ্যাঁ? শপিং থেকে বাইরে থেকে এটা তো তাকে বললাম okay. So well, let me check whether my sound is mute. Oh,
Sir, we cannot hear you. Sir, I think you muted yourself.
okay. Now can you hear me?
Yes, yes, sir.
Okay. Now this transient analysis is for input output variation. Now let me change this capacitance to resistance. What will happen? So I can resistance is what is not visible. Oh, I need to resistance resistance now guardhausen. Now I also 10K 10K same value 10 10K here and 10K up there. I can make it little bit zoom so that it will be bigger. So both resistance are 10K. Now if I simulate, now the input is 1 volt and this is zero point 0.5 because the resistance are equal. And peak occurs at the same location. Zero crosses at the same location. That means there is no phase shift. Is it right? This is the transient analysis. Because we are going to study the frequency response, so this transient response will not help. So therefore, we need to go back to capacitance again. Capacitance C and R. So I just use 100 nano. Now, I can choose this. I change this edit simulation to AC sweep. AC sweep means now we are going to vary frequency and logarithm scale because our frequency is very high, low to high. So what is this is not showing the right panel. I can okay, what happened? Okay, I just use a new simulation. AC AC 2 AC is but I cannot right panel I cannot because I'm not sure. Start frequency. Oh, I don't know why it is not visible to right hand side. I can start with 1K, but I'm not in frequency 10 MP mega, and I let me see. Okay, then so because I have, it is better to choose this source and use this AC source, AC, because I choose sinusoidal, it does not allow me to change the frequency. So BAC, BAC. So because that one is a fixed frequency, so therefore I was not allowed to change the frequency. Now I can edit simulation, time the AC sweep. So still, I don't know what happened to my frequency. I cannot see. Okay, I close this one. I save this one and close again and restart it. Save yes to all. So open. I can open project. PSpice edition. No, cannot see. Okay, right hand side cannot, because I cannot see. Okay, I can write 1. Although I am not visible, so I can write 1, 10 giga, and points per decade, I place 10. Okay, I set start frequency 1. Now I change the output here and simulate. So now this is output response. My start from 1 kilohertz and goes to up to 10 kilohertz. So this is the low pass circuit. Because our magnitude plot is based on decibel, so we need to see response in dB. So I just in between I place D dB. So now I convert this output to decibel dB I put. Now this is the decibel.
Hmm.
So and the slope of this line supposed to be 20 dB per decade. Is it right?
Hmm. Yes, sir.
20 dB per decade. Also, we need to,
Where did you select that DB?
okay, look at here. I placed the dB in the bottom. Okay.
Yeah, how can we select this? Sorry, I didn't see.
I just
Oh,
double click, then
hmm.
it will appear. Is it
Okay,
right?
okay, okay, sir.
So dB. So, so this is basically this one. Now also this is magnitude. Also, I need to draw the both plot is magnitude and phase.
Frequency.
This is magnitude versus frequency and also phase versus frequency. So now it is better to I add another plot.
Plot.
So now this is another window is coming. Then if I okay now if I okay then I add this output. I click okay select this one. Now I will say add trace. You can see add trace. I
Hmm.
can add trace. So what add trace I need to check? So I need to select this. I can copy everything and I can add trace. I place here. So this is the same thing. What happened? Okay, bottom there. So I just place bottom. So this is the replica of same. Bottom and up are same, but now I need to convert this to phase.
Sir, sir, we can't hear you. Something is wrong with the signal.
Hmm. Which signal?
We can't hear you, and your video is also
Okay,
paused.
okay. Now because my mouse. Okay, then wait.
Sir, you muted the mic.
Yes, because my keyboard is close to me, so sometimes it plays.
Okay, okay.
So now you can hear me. Is it right?
Yes, sir.
So because I need to now what I change the magnitude, which is dB, is going to change to
Two.
P. P means phase.
Phase.
Okay, now it's supposed to be uh, and our, as I mentioned, for RC network, phase varies from 0 to 90 degrees. So this is the 90, and this is the, is it right? and the slope of this one is 45 degree per decade. Correct?
Oh.
So, so for example, this is 45. So this is 100 to, so this one decade is 45. Now, this is the magnitude
Hmm.
and this is the phase, correct? And if you look at here, so slope, so one decade, 10 kilohertz. Or for example, here to here is around 20 decade.
Hmm.
So, but now what is the bandwidth of this amplifier or the circuit? Amplifier of the bandwidth is the 3 dB less. So if we click here, then so now I can select. So this is the window. So I can cut the rope, then this is you can see the value. Is it right? The frequency changes and and this is minus 3 dB. Minus close. Now this is minus almost in the upper. So this is almost minus 3 dB.
Hmm.
So this is the cutoff. There is a one notation. When I click and it mentioned the frequency, cutoff frequency is here, though not very clear. And also this is the dB. So, but I can change this level to further to minus 100 so that it can be more prominent. Is it right? 0 to, so this is the minus 3 dB from, so this is the cutoff frequency. So for example, if I change this one to user defined, so minus 90, I can set. So this is 90. So I can figure this one. So this is the RC network simulation. Now if we look at the slope here, okay, here to one decade. So 10 kilohertz. So this is 20 dB. This location, well, if I press here, oh no, I need to change here. And this is minus 35 dB. Now I can go to this another look, one decade. It is 75 dB. But why it shows the 40 dB change? This is 40 dB change. Is it right? 40 dB or 20 dB? 35
Hmm.
to 75, 40 dB change.
35.
A 35 here, and
Hmm.
this is 75. That means
40 dB.
40 dB change. I don't know why this is happening. Supposed to be 20.
20.
Okay, let us increase the stage and let's see how the response changes. Now I will add another resistance, or and another capacitance. So not escape. I can choose my saved value from here, another capacitance. So connect this one connect, connect, and connect. So now again, same amount of value, 100. Now let us simulate this one, or this one. So this, so now I change the time to dB, dB. Now this is the first stage response. Let us go to the second output location, this location, and but this location looks like straight line. Is it right?
Yes, sir.
So, but because magnitude is so low, it's 7, so cannot be viewed. Now, you see, so it is immediately reduced. So if we draw the dot plot, dB, so we can see what is the response. So this is not that much prominent. But let us, oh, because my capacitance is too big. You see 100. I forget to place nano. That is causing this lamp. So nano is not equal. Now let me simulate. So now, because of large value of capacitance, this happened. So now if I choose the
DB.
dV, so I can convert into dot plot. Now, in the last stage, I can see also the first stage response at this location. Okay. But this location is so very big. Okay, I just simulate all together what will happen. Now this is the response. So, but I can see this is dB, dB. Oh, even if I don't use the dB notation. So dB. You see the flow path. What is the green one? Green was the first stage, is it right? And red one is the second stage. So now the first stage slope is less than the second stage. So it satisfies our theory, right? Satisfy or not satisfy? So this is, let me take this one location and go to 1 kilohertz. This. So now the, so 52 minus 52 and 31. And if I select this one, the same. Now I change this location. So now minus 36, and I will adjust here. So here. Now this is 40 dB difference, and this is probably 80 dB difference from 52 to 31, double of the frequency. So now this simulation for the passive circuit. But our filter, when we are going to design our filter, it is based on operational amplifier. So then how can we do that? This one. Now I need to simulate based on operational amplifier. I skipped, close, close this one, close this project. Now I put another project. So I use my folder project, not okay. New project. Again, analog location. I use a different, each one for different location. Another create my directory, which is example 2. So, right. So my computer is ready. I need input here. Okay. Create blank presentation. Okay. So now, first I need to design simple inverting circuit first using operational amplifier. So then I need two resistance analog, one resistance here, one resistance here, and I need the operational amplifier. This is, let me take, this is in the evaluation directory eval. So this is 741. So since I'm going to design inverting amplifier, I mirror vertically. When I mirror vertically, minus becomes upward and plus becomes downward. So not resistance, and this is the feedback resistance. And I need the output resistance also for the as a load circuit R. And also this operational amplifier needs plus voltage and minus voltage. That means we need two DC voltage source also. So VDC, VDC, one is plus, one is plus, another is minus. And now I use the transient simulation first to see whether this is a non-inverting amplifier or not. So this is I can use. So now I need to connect all the components. Let me a little bit larger. So view. So now I need to connect by wire. So this is wire. Connect here. So connect here and connect here. Output is connected to here. And this is the load. And this is connect. And also I need the ground. It to be 0, 0 here. Then connect this 0. This is not I just give it with the wire here. And this is also connected to. So this is my inverting amplifier, but I have not connected this. I connect and also this my source also I place in separate location and ground 0, so 0, so this is looking this is connected. This is connected. Now I can connect plus here to here, but this is crossover. I can connect this line this way, but I'm not going to use this additional wire. So because if I do this way, this is a little bit messy. So what I can do, so this is 15 volt positive, and I can write minus 15 volt negative. So instead of changing the polarity. So what I can do, I can select this power notation, then I can choose. So this symbol. So I can choose here and here. So now I connect this one to this location to this location, and I change this name to V plus. So V plus. So this is not plus. So V plus, and this symbol to
B minus.
minus. You can use any notation, it is immaterial. So now what I can do, so B minus, I just copy this symbol, Control C and Control V. So now this B minus, so minus voltage is connected to V minus, and also I can copy this, or I can use, I can copy or bring this symbol. So it is better to open vertically. Now I bring this plot. So now the circuit is complete. Because if we use this way, if there are many parallel options, just we need to use this B plus and B minus. We don't need to add extra wire. So let us simulate this one to 10K. So gain must be 10 times. So I change it. First I change using the dynamic transient analysis. So source the sign. So I change this offset 0, magnitude 1, and frequency 10. So now I simulate first transient AC. So here again I choose a 2 millisecond, 2 cycle. Simulate. So because I don't put any code, so it is not playing. Now I press the port, input side, input voltage, which is 1 volt magnitude. Oh, oh, why is it not showing? See what happened. Okay. Oh, I don't because I use a very low frequency, so that is why it is not showing. And also, suppose to 2 milliseconds. So, so this is one, input is 1 volt. So this is my another 1 volt, and output is supposed to be 10 times more. 10 times now. 10 volt. Is it right? 10 volt. 10 volt or different? 10. Yes. Can you see? This is 10. So this is the output 10 times, and this is 180-degree phase shift. This is inverting amplifier. So now it satisfies our, that means our simulation is correct. Correct or incorrect?
Correct.
Correct. Now I change this circuit to integrator. So how to make it integrator? I can
Add capacitor.
a capacitance. So I just add capacitance across this resistance. Need to connect. Okay, then let me see. So the output is reduced, and also so zero crossing different positions. Is it right? Input 0 and output 0 because there is a some phase shift over. Now, if we need to draw the board plot, then what we need to do? We need to simulate AC sweep. AC sweep. I don't know why the second side is not showing, but I press 10 and I press 1G data and points per digit I press 10. Not sure why this is not showing. So I just start frequency is 1. Then because this is not visual, then 10 become and oh, 10 point apply. So now values now I simulate just close this window, close this window, close this window, close this here. So mention no AC source. AC sweep ignored. Because why this happened? Because we have chosen V sinusoidal, where signal is fixed with 1 kilohertz. That is why it ignored. So that means I need to change this one to V AC, where I can change magnitude is fixed 1 volt, and I can change the frequency. So, so this is the output voltage, and I just ignore the input. So, so delete here. So now I can draw the dB. No, bracket is missing. So this is the magnitude 20 dB, and also because 20 dB because of our gain of 10. 10 means 20 log 10 is 20. And if you look at how to find the cutoff frequency, then and we need to location maximum is 20, then 17. So this is 17. 17 is here. 17 is approximately here. So now this is our corner frequency because 3 dB difference from maximum to here. And our corner frequency is 1.52 kilohertz. Correct?
Yes, sir.
Now, if I see the what is the slope, so per decade, so this is 3. Oh, we can do because this is 1 decade is within here. So we can also find the slope. So 10, we can find. We can, so this is, because this is, we can find the slope of this one. So now can you simulate, sister?
We will try, sir.
Yes, sir.
Okay. Now, this is difficult or easy? Oh, unless you try, it is, looks like difficult. Is it right?
Yes, sir.
Yes, sir.
So, because now I only show you the only one is case, right?
Hmm.
Now, for example, in our, so now this is, for example, if I draw this response, it is 4.3 kilohertz. Now this is
Zero.
0.01 microfarad, and this is 2.5 kilo. Is it right?
Hmm.
Can I simulate this one? Because LM741 is the op-amp, and this is non-inverting amplifier. I change this one. For example, I change this one, and use this value and see what is the response. Okay, I just delete this line and positive mirror vertically.
Vertical.
Now positive goes up and negative goes down. So now if I connect this one, and I can connect this one. So what is the value for this? Let me find from my book. So this is 2.5 kilo, and this is 0.01 micro, and this is 4.4. 8.3 kilo. So now so I can meet this load resistance, or it is better to put some load resistance. Now simulate this one based on this first integrator.
Oh.
Okay. Now I can make it UV. Hmm. So now my bandwidth is much larger. Is it right? So my bandwidth is much larger here. Then if we look at the first stage, so this is, I don't know, board for 700 kilohertz. So if I draw the 700 kilohertz, so 700 kilo is started with mention 10 hertz. Okay, you can choose 10 hertz to 10, 10 to 700. So now this is the wider response, because for this the stage, and the book is for the whole response, so you can get other response for this stage. So now if we add this circuit, what will happen? Can I add now this one?
Yes, sir.
Okay, let me add this one. So I just copy Control C, Control V. Now what I do, I just delete this one, delete this one, delete this one, delete this one, this one. What I can do, I can choose up to this. So then some capacity, no problem. So I can turn it here. Okay. So now select what are the systems, all are coming here. So now let me see what is the both function. Also positive 0.01 and 5.01
Okay.
and 5K in between here. Let's see, it's not selected. Delete here. I can use no more. I need to use resistance. Or so 5K. Right. Okay. So it is better to add another resistance so that it is safe to simulate. So connect, and we need to connect this one to the ground. Now let us simulate and we check the output at this stage. Now simulate. Oh, my capacitance are not connected, so this is giving some error. So this is why also clean button, that means circuit is not connected. So I delete and delete this green, and I can simulate. So why this? Let me check. Oh, this is also another shorted line. This is short. This hole is short. Although I can see the log file and okay. Now let's see. Oh, and also name OS2, and also this is OS2, same name. If the two of them same name, cannot simulate. So, because if I see the log file, what is the log file? Hmm. So view, where is it? Okay. Cannot. Okay. Now I need to change this name to. Okay, where is? Okay. So not equally selected. Just view further. Okay, this is U1 and this is U1. So change this name to U2 because this is causing all the problem. Because cannot be same name for all the devices. Now simulate. Okay, let me session log. What is mentioned? Still there is a error. Let's close this one. Close this simulation window. Okay, just where this is it. V1, V1. Okay, let me view session log. Oh, you see, capacitance also duplicate. Last time the transistor operational U1 duplicate, but this transistor also duplicate. So that is why giving error. Now, because this is C1, this is also C1. So I need to change this one to C2. Because once I copy, it copied everything. So now if I simulate, now no error. You see, no error.
Input.
So because if input no need to see because this is I applied the same. But you can see also the input. Input remain
Same.
same, or we can. So this is the output. If you need to see the input, you can add another. So for example, if you need to see the input, so I can use the probe here, and this probe is you see 0. So what I can do, I can copy this one, Control C. I can see in the board plot. I add to plot water and click, and I input, and I need to see in dB. So because input, I need this one delete. So for example, I can also change this axis. So how much? -100 to -100. -100. I just -100. So, but this is okay. -100, -150. Okay, then also 300 is too much, 400 is too much. So I just go, what is this? Minus 100 to 200. Because after 200 is not 200, let me see, 300. Okay, minus 300. So the and because output is 1 volt and remain constant, there is no change, so 0 dB. But output changes with the frequency, right?
Hmm.
Yes.
So now this is now from there I can draw. Now now if I add the third stage, can also add the third stage.
Okay, sir.
Add the third stage, can if I add this stage unit again. Okay, let us try to simulate this one. Copy everything. Control C. Control V. Now this is R6. R6. I make it R7. R7, and I make it 10K. 10K. And this is the unity gain. So I just remove this one. Add another resistance. So when I add in there, so name is automatically changed. 10K. So this is unity gain, and I connect this wire to this wire and escape and delete this. And my circuit is, and also this is feedback with another 5 kilohertz resistance. I add one 5K. So another resistance. So loop is 5K. So, but this option is same, so I just name this U3. Now simulate, I can output this location. Because I use input by input and output together, so causing more problem because so this is, but it is now I draw this one dB. My response is, oh, this is 5K according to this book. 5K. Okay, let me mention 5K. 901. 10K. 10K. Okay, now let me simulate. Hmm. But but this is not matching with the book result. So this is the frequency response of this circuit according to our simulation. So let me see. view, zoom, zoom in, zoom in. So, so at least give some result, but the output 5K.01, so 10K inversion. I check here, here. So this there is some loading effect, and due to the loading effect, so my output is, let me check here. Okay, this is input 0. First stage output. Okay, just clean some cache. Close, close this one. View. So let me. This is my design, and this is. These are all components inside this. So we have the ground, and this is the net list. So we can write also using this. Instead of drawing, we can write this net list. So nothing include, nothing. So this is out. So nothing changed. So but this response is not matching with so our book review. Matching or not matching?
No, sir.
Not matching, is it right? Because it's supposed to be straight and after that. So what happened? It shows that so because they are using LM741 and we are using, although this UA741, and this component has much loading effect. And due to the loading, for example, if I go to the first stage and my output is remained same, but first initially what we have simulated, if I add, uh, if I simulate, okay, because no, okay, just undo. Now I remove this feedback resistance. Let me see what happened. So feedback resistance. So now I remove the feedback resistance. I need to check the individual stage for this. Now simulate. So this is without feedback, it is correct. Is it right? So it is the first stage output. Now move to the second stage because second stage. So gain is reduced, but follow the same pattern. And moving to last stage. Also follow the same pattern. Now, if we add the feedback resistance, feedback resistance, uh, feedback resistance, and also because we have added another output load resistance, which cause the loading effect, so we remove this one. So remove the loading effect. So it is exactly same as the our problem. So now I can simulate now. But there is no effect, right? Because this is not matching with this. Now because I can increase the resistance value, let's see, is the effect of this resistance. There is no, only the magnitude is reduced, but this feedback resistance is not so. But if I without feedback, it is matching with this result, right? Matching or not matching? Matching almost. So now you know how to simulate. Can practice this circuit first.
Okay, sir.
So now but if I not so, if you draw the face, for example, just you need to use P here. P, then change this one to phase. And also if you right click property, then you can change the pattern. You can change change this color, the width. So this is, you can change.
Oh.
Also for it, for the properties, if you change this one, you can change the line type also, you can change. But when you need to write a report, you need to capture this picture. Is it right? You need to copy this picture to your Word file. So how to copy? So Windows, then copy to clipboard. Then change white to
Black.
change black. Then let us then I use repeat, then I use the word. Let me see what option. If I choose this option, I control put. So now you can see my result. Is it right? Black become white.
Hmm.
But let us choose another option. Windows, copy to. Now if you use this one, then what will happen?
Black.
So, so this is now little bit lighter.
Oh.
Is it right? So which is screen color. And let me choose the third option, copy to clipboard. Change all our color to black. Then this is become, now all become black. No more color. Now you see this is three different option and three different So in order to write your or present your thing. So now there also you can, if you select this bar, then you can add any point location. So and you can move the cursor and so. If you add some text in the figure, then you can place text, and this is text. Then you can place whatever you like. Right? So, but it is not that much control. But if you using the new version with the license, then you can export this file to data file. From there, you can draw this graph using Excel or other graph plotting program. Can or cannot?
Yes, sir.
So, but for example, what is I have given the link. So, for example, if I go through this PSpice introductory guide, so from this, so what I have mentioned, this step project name, then create blank, part, part list, and select all capacitance, you can resistance and place and do voltage source, make it 0, and and we don't use the offline here. Then and where you can get different components, source library in that library we have voltage source, current source, AC voltage source, and sinusoidal. Analog library we have, although we are not using, and also operational op-amp. This op-amp is the ideal op-amp, which has infinite gain, no internal resistance, no internal capacitance. And analog library, resistance, capacitance, inductor, and so on. And evaluation library, we have this active component. This is not using. And when, how to, for example, for mega, we need to write mega, MEG or MEG. If you write M or capital or M, then it means this is milli. So if a micro, we need to write micro U, nano for N, pico for P, F for femto. Giga, we need to write only G, which is 10 to the power 6. But in the case, the problem is mega. You need to write not M, MEG. So this is, I don't show, later on I'll show. So this is some bias calculation. So this is bias calculator. You don't need the bias. The bias. So this is, so okay, no bias. Now let us do another simulation. For example, for this circuit, for this particular stage, we need to see the output voltage of the first stage. What will happen to our response if you change this resistance value? Okay, so now we need to change this resistance value to different values, keeping all the components same, constant. Then what I need to do, I need to add add spatial parameter. So this is, I'm using parameters here. Then I click this one. So double click. Then in the right click, if I right click, then I can use the pivot, so it shows the vertical. If I right click pivot, it is showing horizontally. So pivot, what I can do, I can add new row and mention this is RES or any name, and I mention this is 4.3K. So now I have defined this parameter as the RES, and this value is 4.3. So now I need to show in my circuit window. So I right click and display. Now we can see, I need to see the name and the value of this parameter. Now when I click, RES is there. Now if I change this one, RES, RES, curly bracket. So that means this value and this resistance value is 4.3. If I simulate for the first stage, so this is the response for our 4K. Now, but I need to change this value to different value. So I edit simulation. Then I can use parametric tool. And I use global parameter. And parameter I have defined as RES, RES, RES. This is the problem of this. I don't know why this is not showing. So this is below also there is another option. So I just use, I need to simulate 4.3K, 43K, 430K. So I use 3 different values of resistance, and I have chosen this. Now if I simulate, then it will simulate for 3 different values. 4.3K. So now we have 4.3K or 43K and 430. So now if I change this one, our response also changes with the variation of the resistance. So, okay, minus 100. So now magnitude is changed. So now it goes for different. Now if I look at here, information, this is for 4.3 kilo. And if I right click the second, so this is for 43 kilo. And if I click here, yeah, cannot. So click here, the information, this is 430 kilohertz, kilo of resistance. Now I can see the variation by using parametric sweep. So can do this one?
that this is too much for today.
No, no. So what now? What you can do? So what I have mentioned up to this, you go and practice. Is it right?
Okay, okay, sir.
And let me check whether it is recorded or not because I have placed the recorded button. And after, okay, it is, okay, stop recording. Stop recording.